Welcome to this problem walkthrough. Today, we'll be tackling problem number 871, minimum number of refueling stops. This is a fascinating problem that involves optimizing fuel usage to reach a destination, and it challenges us to think critically about dynamic programming or greedy approaches. Let's dive in and explore how we can solve this step by step. In this problem, you are driving a vehicle that starts with a certain amount of fuel in the tank, represented by the variable start fuel. The vehicle consumes 1 liter of fuel to travel 1 kilometer. Your goal is to reach a destination that is target kilometers away. Along the way, there might be gas stations where you can refuel. These stations are given as an array stations, where each station is represented by a pair, position_I, fuel_I. Here, position_I is the location of the station along the route in kilometers, and fuel_I is the amount of fuel available at that station. The task is to determine the minimum number of refueling stops needed to reach the destination. If it's impossible to get there, you should return -1. Let's also clarify the input format. The target is the total distance you need to travel, start fuel is the initial amount of fuel in the tank, and stations is a list of gas stations along the route. Each station includes its position and the amount of fuel it offers. The constraints ensure that stations are located between the start and the target, and the fuel amount at any station is positive. The output for this problem is a single integer. This integer represents the minimum number of refueling stops required to reach the target distance. If it is impossible to reach the target, the output should be -1. Let's look at the first example to understand this better. Suppose you start with only 1 liter of fuel, and the target is 100 kilometers away. There is one gas station at position 10, offering 100 liters of fuel. With only 1 liter, you can travel just 1 kilometer. Since the first station is located at position 10, it is unreachable with the given initial fuel, and therefore, it is impossible to reach the target. The output in this case is -1. Now consider the second example. Here, you start with 10 liters of fuel, and the target is 100 kilometers away. There are 4 gas stations along the route, at positions 10, 20, 30, and 60, each offering different amounts of fuel. First, you travel to the station at position 10, using 10 liters of fuel, and refuel with 60 liters, bringing your total fuel to 70. Next, you move to the station at position 20, where you decide not to refuel. Then, you continue to the station at position 30. Here, you refuel with 30 liters, bringing your total back to 70 liters. Finally, you reach the station at position 60, refuel with 40 liters, and have 50 liters remaining. This is enough to reach the target at position 100. In total, you made 2 refueling stops. Let's explore another example. In this scenario, you start with 50 liters of fuel, and the target is 200 kilometers away. There are 3 gas stations along the route, at positions 25, 50, and 100, each offering increasing amounts of fuel. You begin by traveling to the station at position 25, using 25 liters of fuel, and refuel with 25 liters to restore your total to 50 liters. Then, you travel to the station at position 50, where you refuel with 50 liters, increasing your total to 75 liters. Next, you reach the station at position 100 and refuel with 100 liters. After this, you have 75 liters of fuel left, which is sufficient to reach the target at position 200. In this case, you only needed 1 refueling stop. To summarize the example, even though you visited all 3 stations, only 1 refueling stop was necessary to ensure you had enough fuel to reach the destination. This highlights the importance of planning stops strategically to minimize their number while still making it to the target. The problem challenges you to optimize your route by balancing the fuel available at each station and the distance to the next stop. If reaching the destination isn't possible with the given stations and initial fuel, you should return -1. This concludes the problem statement and examples, which set the foundation for solving this optimization challenge. To begin, let's consider the brute force approach. This method takes a straightforward path by trying all possible combinations of refueling stops. At each station, we decide whether to refuel or not, and then simulate the outcomes of those decisions. Essentially, this involves recursively exploring all potential paths to determine the minimum number of stops required. The implementation involves using recursion to simulate each choice at every station while keeping track of the current fuel level, the distance traveled, and the number of stops made. However, the time complexity of this approach is 2 to the power of n, where n represents the number of stations, making it computationally expensive. The space complexity is n, due to the recursion stack. Ultimately, while this method is conceptually simple, it becomes impractical for large inputs because it does not utilize the problem's structure to eliminate redundant states. Next, we have the dynamic programming approach, which is a more structured way to solve the problem. Here, the intuition is to track the maximum distance that can be covered with a certain number of refueling stops, eliminating the need to simulate every possible combination. We define dp, I, as the maximum distance reachable with exactly I refueling stops. Initially, we set dp, 0, to the starting fuel, as no refueling is needed to travel that far. For every station, we then update the dp array in reverse to ensure we don't overwrite results within the same iteration. Specifically, if dp, I, indicates that a station is reachable, we update dp, I plus 1, to reflect the maximum distance reachable by adding the fuel available at that station. Finally, we identify the smallest I such that dp, I, meets or exceeds the target distance. This approach has a time complexity of n squared, due to the nested iterations, and a space complexity of n, for storing the dp array. However, the dynamic programming approach is not without its drawbacks. The n squared time complexity can still be slow for larger inputs, especially when the number of stations grows significantly. Additionally, it requires extra space for the dp array. This leads us to the greedy approach with a max heap, which takes a different, more efficient path. The intuition here is to refuel only when necessary, prioritizing stations with the largest fuel reserves. A max heap is used to efficiently track and retrieve the best refueling options. As we iterate through the stations, we push the fuel available at each reachable station into the heap. When the current fuel is insufficient to proceed, we extract the maximum fuel option from the heap, refuel, and continue. This strategy minimizes the number of stops by always choosing the most impactful refueling option at critical points. The greedy approach offers significant advantages in terms of efficiency. Its time complexity is n log n, where n is the number of stations, due to the log n cost of heap operations. The space complexity is n for the heap. Compared to dynamic programming, this approach is faster because it avoids quadratic updates and uses less space. However, it does have some challenges. The implementation is slightly more complex, as it requires careful management of the heap and proper handling of edge cases, such as when the target is unreachable. Despite these challenges, the greedy approach is an effective way to optimize the number of refueling stops while maintaining efficient performance. After evaluating the different methods, we chose the greedy approach with a max heap as the most suitable strategy. This method strikes the best balance between time complexity and space usage. The brute force approach, while simple to understand, is computationally impractical due to its exponential time complexity. The dynamic programming approach, though more efficient, becomes less practical for larger inputs because of its n squared complexity. The greedy approach, in contrast, directly addresses the problem's goal of minimizing refueling stops by prioritizing the largest fuel reserves whenever needed. By processing stations in order and using a max heap to select the best refueling options, this method ensures that only reachable stations are considered. This approach avoids unnecessary computation while achieving an optimal solution. It trades off pre-computing outcomes, as seen in DP, for faster execution and better scalability. The final complexity for this approach is n log n in time and n in space. This makes the greedy approach both efficient and scalable, making it the ideal choice for solving the problem. By focusing on minimizing the number of refueling stops with strategic decision-making and efficient data structures, this method ensures that we achieve the best performance possible for a wide range of input sizes. This problem challenges us to determine the minimum number of refueling stops required to reach a target distance with a vehicle that has limited fuel capacity. We're given the starting amount of fuel, the target distance, and a list of gas stations, each with their position and available fuel. If it's impossible to reach the target, we should return -1. To tackle this, the brute force approach relies on exploring all possible combinations of refueling stops. The intuition here is straightforward. For every gas station we encounter, we simulate the decision to either refuel or skip, and recursively calculate the number of stops needed for each choice. This will eventually allow us to identify the minimum number of stops required. To implement this, we define a recursive function, DFS, which takes the current position, the remaining fuel, and the number of stops made so far as parameters. This function will simulate the journey step by step, exploring all possible paths to the target. When implementing the recursive function, we define two key base cases. First, if the current position plus the remaining fuel is enough to reach the target, we return the number of stops made so far as a valid solution. This represents a successful outcome. Second, if the remaining fuel is insufficient to make further progress, meaning we can neither reach the next gas station nor the target, we return infinity to indicate failure. Beyond these base cases, the function performs recursive exploration. For each gas station ahead, we first check if it's reachable with the current fuel. If it is, we then simulate two scenarios: refueling at the station and updating the remaining fuel accordingly, or skipping the station and proceeding with the fuel we have. For both scenarios, we recursively calculate the number of stops and track the minimum value among all valid paths. This gives us the optimal solution. Finally, we handle edge cases, such as when no gas stations are provided, by ensuring these scenarios are considered in our logic. The algorithm also accounts for cases where the starting fuel is already sufficient to reach the target, in which case no stops are needed, and we return 0. Additionally, if the gas stations are positioned too far apart to be reachable, the function correctly identifies that the target cannot be reached. The pseudocode captures all of these details. It starts by checking the base cases, whether the target is reachable with the current fuel or if further progress is impossible. The function then iterates over the list of gas stations, evaluating whether each is reachable. If a station is reachable, the function recursively calculates the minimum stops for scenarios where we refuel or skip the station. The results of these recursive calls are compared to determine the minimum stops needed. The algorithm concludes by returning the result of the initial call to the DFS function, and if no valid path is found, it returns -1. This implementation highlights the brute force nature of the approach, as it explores every possible path to solve the problem. Analyzing this brute force approach reveals some key insights. First, the time complexity is exponential, approximately 2 to the power of n, where n is the number of gas stations. This is because the algorithm explores every combination of refueling decisions. As a result, the approach is computationally expensive and inefficient for large inputs, primarily due to redundant calculations. Despite this inefficiency, the brute force method is useful for understanding the problem and verifying results for small-scale inputs. In terms of data structures, the recursive call stack plays a critical role, as it stores the state of each decision during the exploration process. The depth of recursion corresponds to the number of gas stations. Additionally, the list of gas stations, which includes their positions and fuel amounts, is repeatedly iterated over during the recursive calls. To address the inefficiency, we can introduce optimizations such as memoization. By storing the results of previously computed subproblems, we can avoid redundant calculations and significantly improve performance. Memoization ensures that each unique state, defined by the current position and remaining fuel, is computed only once, saving valuable computation time. Another optimization involves adopting a greedy approach. Instead of exploring all combinations of refueling decisions, we use a priority queue to always refuel at the station offering the maximum fuel within reach. This significantly reduces the time complexity, making the algorithm more scalable. It's also important to handle edge cases effectively. If no gas stations are provided, we check whether the starting fuel is sufficient to reach the target. If it is, we return 0, otherwise, we return -1. For cases where no stations are reachable due to distance constraints, the function should also return -1. Finally, we must handle scenarios where the fuel available at a station is just enough to reach the next station or the target, ensuring the algorithm correctly identifies these scenarios as valid solutions. These optimizations transform the brute force approach into a more practical solution while maintaining correctness. Here, we start by importing the Heap module, which we'll use to manage a max heap. This is essential because we want to prioritize refueling from stations that offer the most fuel. We then define the min refuel stops method, which takes three inputs: the target distance, the start fuel available at the beginning, and a list of stations, where each station provides its position and the amount of fuel it offers. Next, we initialize a max heap as an empty list, as well as some key variables. Fuel keeps track of our current fuel level, starting with start fuel. Stops counts the number of refueling stops we've made, and prev_position tracks the position of the last station we passed. Now, we begin iterating through the list of stations. For each station, we calculate the fuel consumed to reach it by subtracting the distance traveled, which is position prev_position, from the fuel variable. If our fuel becomes negative, it means we don't have enough to reach the current station. In this case, we repeatedly use the station with the largest fuel in the heap by popping from the max heap, converting its negative value back to positive, and adding it to our fuel. Each time we do this, we increment the stops counter. If we run out of stations in the heap and still don't have enough fuel, we immediately return -1, indicating that the target can't be reached. Finally, if we have enough fuel to reach the current station, we add the station's fuel to the heap, storing it as a negative number to maintain the max heap property. After processing all the stations, we update the prev_position to the current station's position. At this point, we need to handle the remaining distance to the target. To do this, we subtract the distance from the last station to the target, which is target prev_position, from our remaining fuel. If the fuel becomes negative, we again use fuel from the max heap, prioritizing the station with the largest fuel available. For each refuel, we add the station's fuel to our total and increase the stops counter. If we exhaust all available refuels and still don't have enough fuel to reach the target, we return -1 to indicate failure. Finally, if we manage to have enough fuel after these adjustments, we return the stops counter, which represents the minimum number of refueling stops required to reach the target. This ensures that the function accounts for all possible scenarios efficiently while leveraging the max heap to prioritize the most beneficial refuels. Here, we begin the Java implementation for solving the minimum number of refueling stops problem. To manage the fuel efficiently, we use a max heap, implemented with a priority queue, to store the fuel amounts available at visited stations. This allows us to always access the largest fuel amount when needed. We start by initializing the fuel variable with the starting fuel, setting the stops counter to 0, and tracking the previous position as 0. Then, we iterate through each station, which is represented as an array containing the position and the fuel available at that station. For each station, we calculate the fuel required to reach its position by subtracting the distance traveled from the current fuel. If the fuel becomes negative, it means we can't reach the station with the available fuel, so we repeatedly refuel using fuel from the max heap until we have enough fuel or the max heap is empty. Each refueling operation increments the stops counter. If we run out of fuel and the heap is empty, it's impossible to proceed further, so we return -1. If the fuel is still less than 0 after attempting to refuel with all available options, we return -1, indicating that reaching the target is not possible. Otherwise, we add the fuel available at the current station to the max heap, as it might be useful for future refueling needs, and update the previous position to the station's position. After processing all stations, we handle the remaining distance to the target. Similar to earlier, we subtract the distance to the target from the current fuel and refuel from the max heap if necessary, incrementing the stops counter each time. Finally, if the fuel is sufficient to reach the target, we return the total number of stops made. If not, we return -1, indicating that the target cannot be reached even after utilizing all available resources. To start, we are given the target distance of 100, an initial fuel of 50, and 3 fuel stations positioned at distances 25, 50, and 75, each offering some amount of fuel. We begin by initializing our variables. The current fuel is set to 50, the stop count is 0, the previous position is 0, and we use an empty max heap to manage the fuel available at stations. At the first station, located at position 25, the distance traveled is 25, leaving us with 25 units of fuel. We add the available fuel from this station, 25, to our max heap as -25, so the heap now contains -25. We then update our previous position to 25. Next, at the second station at position 50, we travel another 25 units, which depletes our remaining fuel to 0. We then add the fuel from this station, 50, to the max heap as minus 50, making the heap contain minus 50 and minus 25. The previous position is updated to 50. At the third station, located at position 75, we attempt to travel another 25 units. With 0 fuel remaining, we find that we are short by 25 units to reach the station. At this point, we refuel using the max heap by popping the largest element, which is minus 50. This gives us 50 additional units of fuel, bringing our total to 25 and increasing our stop count to 1. After refueling, we push the 25 fuel from this station into the max heap as minus 25, so the heap now contains minus 25 and minus 25. The previous position is updated to 75. Finally, we calculate the distance to the target, which is another 25 units. With exactly 25 units of fuel, we reach the target successfully. The total number of stops required is 1. In this example, we aim to reach a target of 200 with an initial fuel of 50 and 3 stations positioned at 50, 100, and 150, each offering 50 units of fuel. We start with the same initialization as before, fuel is 50, stops are 0, previous position is 0, and the max heap is empty. At the first station, located at position 50, we travel 50 units, depleting our fuel to 0. We then add the 50 fuel from this station to the max heap as minus 50, so the heap contains minus 50. The previous position is updated to 50. Next, we aim for the second station at position 100, requiring another 50 units of fuel. Since our fuel is insufficient, we refuel by popping the max heap, which provides 50 additional fuel. This brings our total fuel back to 0, increases our stop count to 1, and leaves the max heap empty temporarily. We then add the 50 fuel from this station into the heap as minus 50, so the heap again contains minus 50. The previous position is updated to 100. Now, to reach the third station at position 150, we need another 50 units of fuel. Again, our fuel is insufficient, so we refuel using the max heap. Popping the heap provides 50 additional fuel, bringing our total back to 0 and increasing our stop count to 2. The fuel from this station is added to the heap as minus 50, leaving the heap containing minus 50. The previous position is updated to 150. Finally, we aim for the target, 50 units away, but once again, our fuel is insufficient. Refueling one last time from the max heap adds 50 fuel, bringing the total to 0 and increasing the stop count to 3. With this, we successfully reach the target. The total number of stops required is 3. In contrast, for the final example, we attempt to reach a target of 100 with just 1 unit of fuel and a single station at position 10 offering 100 fuel. Here, we cannot even reach the first station, as the required distance of 10 exceeds our initial fuel. With no fuel in the max heap to refuel, reaching the target is impossible, so the output is -1. To analyze the time complexity of our solution, we start by considering the iteration through the list of stations. If there are n stations, this step requires a single pass over the array, resulting in O(n) time. Next, we account for the heap operations performed during refueling. At each station, if we are out of fuel, we may need to perform a heap pop operation to retrieve the station with the largest fuel amount stored in the max heap. Since the heap size is bounded by the number of stations visited, and each heap pop takes O log n time in the worst case, performing this operation for all n stations contributes O and asterisk log n to the time complexity. Additionally, for each station, we push the fuel amount into the heap, which is another O log n operation per station. Over all stations, this adds another O and asterisk log n to the time complexity. These heap operations dominate the overall time complexity of the algorithm. After processing all the stations, we still need to evaluate the remaining distance to the target. If additional refueling is required, this might involve up to n more heap operations, each taking O log n, contributing another O and asterisk log n in the worst case. Combining these steps, the total time complexity of the algorithm is driven by the heap operations, which amount to O and asterisk log n. Adding the O, n, from the linear iteration through the stations, the overall time complexity remains O and asterisk log n. Now, looking at the space complexity, the primary factor is the max heap used to store fuel amounts. In the worst case, all n stations' fuel amounts might be pushed into the heap, leading to a space requirement of O(n). Other variables like fuel, stops, and preb_position use only constant space, or O(1). Thus, the total space complexity of the solution is O(n). The overall space complexity is dominated by the size of the max heap, meaning it is O(n). To put this in perspective, we can compare the optimized solution to a brute force approach. A naive approach would involve testing all possible combinations of refueling stations to find the minimum number of stops, which would require evaluating all subsets of stations. This results in an exponential time complexity of O(2 to the power of n), as we would need to explore every subset. The space complexity in this case would still be O(n), either due to the recursion depth or to storing intermediate results. In contrast, the optimized solution leverages a max heap to prioritize refueling from stations with the largest fuel amounts. By maintaining this heap and iterating through the stations, we achieve a much more efficient time complexity of O(n*log n and a space complexity of O(n), making this approach significantly better than the brute force method. Breaking down the best, average, and worst-case scenarios, we see how the algorithm adapts to different inputs. In the best case, the starting fuel is sufficient to reach the target without any refueling. Here, the algorithm simply iterates through the stations, resulting in O(n) time and O(1) space. In the average case, some refueling is needed, but not excessively. The time complexity remains O(n*log n due to the heap operations, and the space complexity is O(n). Finally, in the worst case, we need to refuel as many times as there are stations. This results in O(n*log n time, with the heap containing all stations' fuel amounts, leading to O(n) space complexity. Mathematically, the dominant term in the time complexity is the heap operations. With n stations, we perform up to n insertions and n deletions, each taking O(log n). Thus, the total cost of heap operations is 2*n*O(log n), which simplifies to O(n*log n). Adding the O(n) for the linear pass through the stations, the overall time complexity confirms to be O(n*log n, while the space complexity is determined by the heap size, which is at most O(n). When working on this problem, there are some common pitfalls to watch out for. First, ignoring edge cases can lead to incorrect solutions. For example, consider scenarios where there are no refueling stations at all, or where the initial fuel is not enough to reach the very first station. Even situations where the fuel is just barely sufficient to reach the destination can expose flaws in your logic. Testing these edge cases explicitly is crucial. Next, inefficient approaches can be a major issue, especially with large inputs. Brute force methods, like trying all possible combinations of stops, can result in timeouts for constraints as large as 10 to the power of 4. Instead, focus on optimizing with greedy algorithms or dynamic programming. Misunderstanding the problem requirements is another frequent mistake. For instance, the goal might be to minimize the number of stops, not to maximize leftover fuel, so be sure to carefully read the problem statement to align your solution with the actual objective. Off-by-one errors are also common, particularly with zero-indexed fuel stations or when calculating distances between stations. These small mistakes can lead to big inaccuracies, so double-check your indexing logic. Finally, overcomplicating the solution can be tempting. Adding unnecessary layers of complexity or combining multiple approaches can make debugging and testing much harder. Start with a simple, clear plan and build on it incrementally if needed. Now, in an interview setting, it's important to not only solve the problem but to communicate your thought process effectively. Begin by explaining the brute force solution, as this demonstrates your understanding of the problem's fundamental structure. Then, transition to discussing optimizations, such as using a greedy algorithm or dynamic programming. Identifying patterns is another key skill. Optimization problems often involve trade-offs, and in refueling scenarios, you'll need to weigh current fuel reserves against future needs. This naturally lends itself to a greedy approach, where you prioritize the largest fuel gains at critical moments. It's also valuable to explain the trade-offs involved in your solution. For instance, if you're choosing between multiple approaches, compare their time and space complexities, and justify why your choice is the most efficient for the given constraints. Testing edge cases is just as critical in interviews as it is during your own problem solving. Bring up examples like empty inputs, minimal constraints, or extreme values to show you're thinking holistically. Additionally, understanding related problems can give you a broader perspective. For example, this problem is directly connected to other optimization problems like Jump Game 2, which also minimizes steps, or Gas Station, which involves completing a circuit with limited fuel. These connections can help you recognize patterns and techniques that are widely applicable. There are also alternative approaches to solving this problem, each with its own strengths and trade-offs. The greedy approach is a popular choice because it focuses on prioritizing the largest gains. For example, refuel at the station, offering the most fuel when you need it. This is often optimal for problems aimed at minimizing stops, but it does have limitations. Greedy methods can fail in scenarios requiring global optimization, where skipping a high fuel station might lead to better outcomes later. Another method is dynamic programming. Here, you might define states like dp, I, j, which represent the maximum distance reachable with I stops and j fuel. While this approach can be very effective when constraints are tight, it comes with higher space complexity and can be harder to implement. Lastly, using a priority queue or max heap is another efficient strategy. This allows you to simulate greedy decisions, such as always choosing the station with the highest fuel available when you stop. While slightly more complex to code, this method strikes a balance between clarity and efficiency, making it a strong choice for many scenarios. Each of these approaches has its place, so understanding when to use which one is key to mastering problems like this. Great job! We've covered the solution to minimum number of refueling stops and discussed both the brute force approach and optimization strategies. Remember, understanding the principles behind dynamic programming and greedy algorithms can be a game changer for these types of problems. Keep practicing, and we'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!